molecular dynamic simulation? So what is molecular dynamic simulation? So it is a computer simulation method for analyzing the physical movement of atoms and molecules. The atoms and molecule are allowed to interact for a fixed period of time, like for nanosecond or picosecond, whatever a time you will run, and giving a view of the dynamic evolution of the system. So in most common version, the trajectories of atoms and molecule are determined by numerically solving Newton's equation of motion for a system of interacting particles, where forces between the particle and their potential energy are often calculated using interatomic potential or molecular mechanical force field. So let me show you how. So whenever this is defined as a simple, you can see uh, from uh, yes, this that particles are interacting in this way that and like this atoms usually interact with each other, and similarly the macromolecules are also interact and are always in the dynamic motion. So what are the steps? The very first step is that you have to use the PDB file of protein, so which you can download from like Discover Protein Data Bank. So which I have already shown you how you can download any PDB file. Just go to that RCSB PDB and write down your protein name or PDB ID, and you will get that. And you have to download that protein, and you have to clean the protein. So the PDB file should contain only protein atom. It should not contain any water molecule or any ligand atom, so that or and is ready to be the input into the first GROMACS module, that is PDB2GMX. So we are going to use GROMACS for simulation. So its first module is PDB2GMX. So the purpose of this PDB2GMX is to generate three files. That is, the very first is the topology file of the molecule, and the second is the position restraint file, and third, which is post-process structure files. So the topology file, which is also called as topol.top, by default contain all the information that is necessary to define the molecule within a simulation. And this information include non-bonded parameters like atoms, type, and charges, as well as bonded parameters, that is bonds, angles, and dihedral. And you can do this by executing the command, which is gmx pdb2 gmx. This command as it is written. So this is the your clean.pdb, the protein which is already clean. And then the output dash o is for output, which generate your process.grow file and water SPC. Okay, so let me show you. So you cannot do it in your own system because the simulation is computationally very expensive or process. So you cannot do that in your system. So we have here, we are going to use workstation. So we have this PDB file. You can see that this is our PDB file. And now we are going to execute the very first command, that is PDB2GMX. You have to open it in terminal and just type this command, the name of your protein, and then output will be. And then you have to select the force field. Now we are going to select the 9, which is the force field for uh, our system, so that you have to see what force fields you are going to use. So after this command, so after the executing of this command, uh, we have this process by this PDB2GMX. We will have to choose that force field, which I have already shown that how you have to choose this force field. And the force field will contain the information that will be written to the topology. And this is a very important choice. You should always read thoroughly about each force field and decide which is the most applicable to your situation. And you so now you can we will have this new file generated, that is processed.grow, topol.top, and postre.itp. So what these files contain is that this process.grow is a GROMACS formatted structure file that contain all the atom defined within the force field. That is, hydrogen atom have been added to the amino acid in the protein. Topol.top file is the system topology. More on this in a minute. So we will see that. And postre.itp file contain information used to restrain the position of heavy atom. Then next step is we will define the unit cell and we will add the solvent molecule. So there are two steps to define the box and filling it with solvent. That is, the define the box dimensions using the edit conf module and fill the box with water using the solvate module. For example, like we are going to use this gen box. So in this, we will be using the command. So let's define the box using this edit con. This is the command, that is gmx edit conf -f process.grow, which is the file already we have developed in the previous by the previous command, and that will be the input for this, and the output will be the new box.grow, and we have to define this cubic. So the above command centers the protein box, that is by -c, this is which we are using, and places it at least 1 nanomolar from a nanometer from the box edge. That is, we are defining it by -d. So the box type is defined as -bt cubic. You can take any box like orthorhombic and other. So the distance to the edge of the box is an important parameter. So this is the important parameter, and since we will be using periodic boundary condition, we must satisfy the minimum image convention. This, and that is, a protein should never see its periodic image, otherwise the forces calculated will be spurious. And specifying a solvate box distance of 1 nanometer will mean that there are at least 2 nanometer between any two periodic image of a protein. This distance will be sufficient for just about any cutoff scheme commonly used in simulation. So once we will define the box, we will have to solve it, fill it with solvent. Like here, we are going to use water molecule, and you can use any solvent. We are creating like experimental kind of this thing in our system. So solvation is accomplished by using the solvate, this command, that is gmx solvate -cp. So the configuration of protein is for this cp is contained in the output of the previous edit conf step, and the configuration of the solvent, that is dash CS, which we are seeing here, is a part of a standard GROMAX installation. And we are using SPC 216.GRO, which is a generic equilibrated 3-point solvent model. So you can use SPC 216.GRO as the solvent configuration for SPC, SPC-E, or tip 3P water, since they are all 3-point water models. So you can choose any of them. So the output is called this solve.grow, and we tell solvate the name of the topology, that is topol.top, so that it can be modified. So now let's use another command, and I have written this command over here. This is, we are defining the box now. And then we are going to add solvent, that is, we are going to use water molecule. So now we have already now the next step is adding ion. So now we have a solvated system that contain a charged protein. The output of PDB2GMX told us that the protein has a net charge of 10 plus 10 based on its amino acid composition. If you miss this information in the output, you can look in the atom section. And it should read in the part this like this Q.8. Since life does not exist as a net charge, we must add ions to our system. So the tool for adding ion within GROMAX is called Geneon. And what Geneon does is read through this topology and replace water molecule with the ion that the user is specifying. So the input is called a run input, which has an extension of .ppr. This file is produced by the GROMAX GROM module, which will also be used later when we run our simulation. So what GROMS does is process the coordinate file and topology to generate an atomic level input, that is .ppr. So the .ppr file contains all parameters for all the atom in the system. To produce a .ppr file, we need an additional input file, that is .mdp file. MDP is molecular dynamic parameter file, and this will assemble the parameter specified in the .mdp file with the coordinates and topology information to generate a .ppr file. So .mdp file is normally used to run energy minimization or an MD simulation, but in this case is simply used to generate an atomic description of the system. So assemble your .ppr with the following, like we are going to use this command. Um, gmx grom dash f ines.mdp. MDP file is what, which we are going to have this input parameter we will specify in this, and which will this have this output in the form of this ine.tpr. And topology file is already your topol.top, which we will be using. Now we have an atomic level description of our system in our binary file ines.tpr. We will pass this file to Geneon. So this file will be used as input for the next step, and then this will produce solve ines.grow. And we have to specify the name, that is p name and N name. N name is for negative charge. We are going to use that chlorine, and Na is for sodium. For the positive charge, we are going to use this sodium. So once you will click it, you have to choose 13 for sol, so that you are going to replace this sol, that is the water molecule, for you are exchanging or replacing the sol water molecule with the ion. So as we have seen that dash is as input, generate a .grow file, and dash O for output, process the topology, and dash P to reflect the removal of water molecule and addition of ion, define positive and negative ion, like for I have already told, that is P name for positive and N name for negative respectively. So ion is adding ion is necessary for to neutralize the net charge of the protein. So let's so now we are going to use this add ions by first command, and then we will specify that which ion we are going to use. So Na and Cl, so that our protein charge will be neutral. Here sol, that is in this case we have this 15 number as sol, since our at protein has zinc ion, that is why it is showing on 13 number. So now the next step is energy minimization. So to solve the solvated electroneutral system is now assembled, and before we can begin dynamics, we must ensure that the system has no steric clashes or inappropriate geometry. The structure is relaxed through a process called energy minimization, and the process of for energy minimization is much like the addition of ions. We are once again going to use this GROM to assemble the structure, topology, and simulation parameter into the binary input file, that is .tpr. But this time, instead of passing the .tpr to genuine, we will run the energy minimization through the Gromax MD engine, that is MD run. So this is the command which we are going to use. This is GMX. Yes, GMX GROM dash F minim dot MDP is the MDP file is which we will give at as input file, in which we will define all the parameters for doing this step, and the output will be m.tpr. So you have to make sure that topol.top, that is the file, this is updating when running this genbox and genuine. Otherwise, there will be error will occur. You have to make sure. So now we will run energy minimization step by doing this gmx md run dash v defnum m. Okay. So when we will run it, we will get the following files, that is m.log, m.edr, m.trr, and m.grow. So these are like m.log is the text file for this process, energy minimization process. M.edr is binary energy file, and TRR is binary full precision trajectory. M.grow is energy minimized structure. And there are two very important factors to evaluate to determine if energy minimization was successful. The first is the potential energy, and the second is for density. So these are the values which you have to put for that, like mtol should be around 1000 when you will prepare that MDP file. So now we are going to use this minim.mdp. So you can see here that there is all the files are present. And since we have named it m.mdp, so we will change it. Now we are going to run it by md run. So we will be using this command for energy minimization. So this is once it will complete, we will then proceed further. So now it is done. Let's move to next step. That is equilibration. So we must equilibrate the solvent and ion around the protein. If we were to attempt to change dynamics at this point, the system may collapse. So the reason is that the solvent is mostly optimized within itself and not necessarily with the solute. So it needs to be brought to the temperature we wish to simulate and establish the proper orientation about the solute. That is, we are in this case we are using the protein. And after we arrive at the correct temperature, the basic of that is the kinetic energy. We are going to use that. For example, in this case we are using 300 Kelvin, and we will apply pressure, which is atmospheric pressure, that is 1 atm, to the system until it reaches proper density. So have uh, so have you remembered the postre.itp which we have prepared from the PDB2 GMX in the very first step? Now that is we are going to use over here. That is the purpose of that postre.itp is to apply a position restraining force on the heavy atom of the protein, anything that is not a hydrogen. So the movement is permitted, but only after overcoming a substantial energy penalty. The utility of position restraint is that they allow us to equilibrate our solvent around our protein without the added variable of the structural changes in the protein. The origin of the position restraint, that is the coordinate at which the restraint potential is zero, is provided via coordinate file passed to the dash R option of the GROM. So equilibration is often conducted in two phases. The very first phase is the conduction under NVT ensemble, that is constant number of particle, the volume and temperature. This ensemble is also referred to as isothermal, isochoric, or um, canonical. The time frame for such a procedure is dependent upon the content of the system, but in NVT, the temperature of the system should reach a plateau of at the desired value. If the temperature has not yet stabilized, additional time will be required. Typically, 50 to 100 picoseconds is sufficient, and we will conduct a 100 picosecond NVT equilibration for this exercise. So we will use this command, this GROM, GMX GROM dash and MD run just as we did in EM step. So that is, let's do it. We will proceed for equilibration part 2. So let's go on the next, that is NVT. Then we will run. So it will take some time as we are running it for 100 picosecond. So it will take some time. So till then, let's learn about the second step of this equilibration. If you have any queries, you can ask. Please feel free to ask. Is there any query? So till then, let's learn about phase 2 of equilibration. So since we have already used the volume, stabilized the volume, temperature and all that. So now we are going to use this in isothermal isobaric. Previously, that is the equilibration part 1, we have used isothermal isochoric. Now we are going to use isothermal isobaric. So we have to stabilize the pressure And there's also the density of the system. So equilibration of pressure is conducted under NPT ensemble, wherein the number of particles, pressure, and temperature are all constant. And the ensemble is also called the isothermal isobaric, as I have already told you, and most closely resembles experimental condition. So we are now including the dash T flag to include the checkpoint file. So as you can see, that is dash T nvt.cpt is there. And this file contains all the necessary state variable to continue our simulation, and to conserve the this velocity produced during NVT, we must also include this file. So the coordinate file dash C is the file output of this NVT. And then we will run this by using this command, and then again similarly we will do definum npt. So let's see if our first step of equilibration is completed or not. So it's still running. Till then, let's see the other files. Like, let's see this. These are all sol.grow, eins.grow. And let's see this topol.top. You will see at the end that there is Na is added, sol is there, ein chain is there at the name this compound. And all the files are included. There is also topol ein chain, topol protein chain A file, and similarly postre.itp. So here you will find all the coordinates of this file in the x, y, and z axis. And this is also the specifying about the density and all that. And in protein, you will see that there is different protein, and residues are mentioned over here. And this Q dot tell us about the charge. And their iron, since our protein has zinc ion, so you will see that zinc is there. And there is also that the include chain topologies is that there both the topology is added, that is ion chain topology and protein chain A topology both. Is there any problem or any queries? So now it is completed. So now let's do our next step, that is equilibration phase 2, that is for the NPT. And then we will equilibrate it again for 100 picosecond, and it will take some time. So let's see about uh, the MDP file, that is m.mdp input files which we have provided. This is the m.mdp file in which we have mentioned about different parameters. And then similarly, we have ions.mdp. In this also, we have mentioned about different energy steps and all that. And npt.mdp, in which we have mentioned about the steps also, which we have performed, that number of steps, and all the information about this group, that is protein and non-protein group. And NPT and NVT, we have prepared NVT also. So these are the different parameters which we are going to use in MD.MDP also. Let's open that topol.top, which was the first topology file, um, in which we have this at the end. You can see that protein chain was there and ion was there initially, which has been modified, that you can see as with the hash sign. Then after, then again there is the another modified which will be after that. So we can see that at the end there is sol which is added, and our this which we are using right now, it's like iron is also there, like Na, sodium is there, one at the end. So we can check that is our topol.top is modifying or not, is updating or not. You have to check that, otherwise you will encounter several errors while running. So it is now completed. Now let's come to the final step, that is production MD. That is, you have to run your simulation. So as we know that our system is now equilibrated, and it at the desired temperature and pressure, and we are now ready to release the position restraints and run production MD for data collection. The process is just like we have seen before, and make use of the checkpoint file also. That so this with the flag dash t. So we are going to use with this command. So this will also estimate for the PME load, which will dictate how many processors should be dictated to the PME calculation and how many for the PP calculation. So we have to execute this command by using this gmx definum md, whatever the name of your file should be mentioned here. And if you have this GPU, so you can add at the end, that is dash nb GPU. So let's run. Now we have this md.mdp input file as I have shown you. So that is there. Now we have to just paste this command. Now you will be adding this final run by using the command gmx md1. It will also take some time. So yes, now yes, now it is completed. Now let's go for analysis step. So for doing analysis, you have to use this post processing tool to strip out the coordinates, correct for periodicity, or manually you can alter the trajectory time units, like you can use the time units. If it is in picosecond, you want to rename it as, or you want to, your graph plot should be in nanosecond, so you can change it, or frame frequency also you can change. For this exercise, we will use this TRJ-conf to account for any periodicity in the system, and the protein will diffuse through the unit cell and may appear broken or may jump across to the other side of the box. So to account for such behavior, so we have to use this command. Um, and after using this command, we have to select protein to be centered, and we have to use the system to be for output. And we will conduct all our analysis on this corrected trajectory. Let's look at the structural stability first. And so there is also the GROMACS has built-in utility for RMSD calculation, that is called as RMS. And we will use this command for plotting the RMSD plot. So, and we will be using backbone, that is for, you have to choose 4 for backbone for both the least square fit and the group for RMSD calculation. And this tag, this is TU flag and dash TU flag, which you will see, will result our output in nanosecond. Uh, or if the trajectory is written in picosecond, then this will happen. Let's come to analysis. So let me share it. So now we are going to use this command. So now we are going to use this command, the same trj conf, and this is our XTC file, which is produced after this molecular dynamic simulation, and .tpr is also uh, which we have produced in the course of simulation. And this will be our output, which is no pbc.xtc. So, and our protein will be at the center. For that, we have to choose, let's see, that you will run, and then you have to choose this protein for centering and system for output. So let's choose one for centering, and then for output, you have to choose system and then enter. Now there is this command, this which we have already chosen. So now RMS we are going to use. So we have to choose this 4 for backbone. Then choose 4 for backbone for both the least square fit. Now you can plot this graph, RMSD plot. We are not going to use this crystal structure RMSD, so we are only plotting this one graph. So you can do that by XM Grace and just write the name of that file, that is rmsd.xvg. File is the output, and you will it is shown like this. So since we have run only for 100 picosecond, this is very small, and we have like plotted it in nanosecond, so that is 0.01 nanosecond was there. So is there any problem? So any queries you can ask now. You have 1 minute. Then we will start next session of molecular docking. So you can ask any if there is any queries or any question.
Hello, Nabila.
Yes, sir.
Yeah, are you finished?
Yes, sir. We are going to start next session after 1 or 2 minutes.
Okay,
Is
okay,
there any queries?
sure, sure.
So let's start for molecular docking. Please open your Autodoc Vina tool. So everybody must have that this protein.pdbqt file, ligand file, and con file, right? So you have now. So let's share that. So we have this this five, I said seven, eight which is this protein file, and this ligand file is in PDBQT format, and there is also your con file, right? So now we are going to rename our this 5Z R8 into protein. So please rename it as protein, your PDBQT file which we are going to use. So rename it as protein, and you have ligand. So let's check before proceeding this con file. So your con file should look like this. So please check it, that is it the same values. Okay. So have you everybody renamed your protein 5Z R8 into renamed your 5Z R8 into protein? If you will not rename it, otherwise it will you will get some error, because here we have defined that receptor is equal to protein.pdbqt. So please rename your protein. So let's just copy this protein. Let me show. Copy this protein, ligand, and this con file. Okay, we are going to copy it. And we are going to paste it in uh, Windows C. Click on Windows C, then program files, 86. This is the program file 86. You have to click on that. There in there should be this the Script Research Institute. So click on this, and then you will get this Vina. So click on this and copy that which we have copied. Now paste it. So now we have pasted. Copy the link. Of this folder. Is everyone following? Do let me know if you're following or not. Has everyone reached till this point? So, shall I proceed? Okay, um, so the copy this path and then open your CMD and run it as administrator. So you will now get this. Yes, Tareen, we have to copy our protein.pdbqt, ligand.pdbqt, and con file into this Vina, which is in Windows C, and you will get in the folder program files 86, and in that you will get this the script research institute and then Vina. So you have to copy that, and then you have to copy that path also. Let me tell you this. You will you have to copy this and paste it over here, this protein which you have already renamed your this 5Z R8 protein, you have renamed it into protein, then ligand, and then conf. You have to paste it over here, and then please copy this, click on it, and this will be shown like this. Then right click on it and copy this. Then you have to open, write in your type on search CMD and open your command prompt and right click on it, run it as administrator. Okay. If you will not run it, then you will encounter error. So run it as administrator. So this my command prompt is open. So everyone has reached over here. Tareen, have you reached over here? In lower tab in your system, search CMD or command prompt, then right click on it and run it as administrator. Then your this dialog box will appear. Okay, done. So have you run it as an administrator? Okay, then it's fine. Then we can proceed. So there is this you have to type over here, CD dot enter. Then cd dot again enter. Then cd space and then paste your path which we have copied. Then enter. Then just write P and press tab. Then you will, once you reach over here, this program file 86, then stop. Then again press backspace, then this, then write T. Then again search this by using tab. Then V and then press tab. Then you will get over here. Then again backspace. Then write Veena dot exe dash dash config conf dot txt dash dash log dot txt. So this is a config. So it will show you like this. I'm uh, so as you can see now it is completed, and this will give you result in the form of affinity into kilocalorie per mole, also called as autodoc energy. So you can see in the Vina folder, let's go into the Vina folder and we will see there that we will get two file, that is out and log file. So let me share that. So here this is the new two output. This is the output file which we got, and this is the log file. So you can copy these two. Is it visible now? So you have to just copy your log and out file, which we got the result after result. So just copy it and paste it into the folder which you have made for this workshop. So I'm pasting it over here, my workshop folder. So now this two files, which is log and this out file, it's the result which we got. So now let's open our out file with Discovery Studio software. So once you will open this out file into the Discovery Studio, it will be visualized like this. You will get this 10 model. Like this is the model number 0. This is the next model. This is the next. This is the next. So you can see that this you get it into the 10 different models are there of the ligand. Now let's open our this protein file, which is 5ZR8. Now go to in the window explorer and just open your this 5ZR8 file, which is your PDB file which you have cleaned. This file and copy it and paste in the same folder and rename it as result. So, and now just this result one, open it in your Discovery Studio. This is the same protein which we have cleaned on the very first day. And with this protein, we have made this PDBQT file. Now we are going to use this protein for result. So uh, as we have seen that the first, you can see from this command prompt, like this command prompt, the first one a molecule is showing the lowest energy, that is the minus 6.4. As you can see that the first one is showing minus 6.4, second molecule is showing minus 6.2, third one is also showing minus 6.2, and fourth minus 6. So the lower the energy, the best will be the molecule. So we are going to use this first molecule, which is having the lowest energy, that is minus 6.4. So let's go to Discovery Studio software where we have opened the out file. Now this is our out. Yes, here the model number 0. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is there, as we have already seen from that command prompt result. So we are going to choose this first molecule, which is found to have the lowest energy, that is minus 6.4. And we are going to right click on it and then copy this. So after copying, go to this result where you have this PDB file. Then click on this arrow and then paste in the section. So you will get your result over there. Now you can go for the mouse mode and rotate it. So this is your protein and ligand file. So this is your result. You can change its background color. Let's change it just by clicking on white. Let's change its background color to white. So is there any problem? Everyone is following? If there is any problem, let me know. So this is our result. Now you can unclick it, this box, and your ligand will disappear. And then go to section, their structure section. And click on the structure. Then you can add surface and click on OK. So this your protein structure will appear. And now let's just click this box so that our ligand will appear again. So this, so now you can see that ligand is binding at this cleft in the active site of the enzyme, as you can see from this. Now let's change the color of protein. Let me select the protein. You can select both the chain and then click on this and your color, and then click on color, and then let's change it to this color. Then let's click on OK. Click on this surface atom charge and then click on color and OK. Then your this protein will explain the color you want. You can change or do any color. Now let's change the color for ligand molecule as well. So just click on this ligand. This will be highlighted with the yellow color, as you can see. Now right click on this, then go to again to the color and let's color it um, green. So as you can see that this is your protein, and in the cleft there is ligand is binding. And you can save this as your image just by clicking on the file over here. You go to the file and go to save as, and then click on this add image file. Click on this and then save it. Then this dialog box will appear where you can set your this height and width and unit. Also you can change and do changes as you want, and just click on OK. Then that must be saved. Let's go to the folder and check. So now we have we can see that this is a result PNG file. Let's click on this. Then you can see that this is the image which we have saved. You can do any change. You can change the structure, color, background, and lot of more thing as well. So is there any problem? If there is any problem, let me know. You can also do different other style, like you can delete this soft color, then your protein is, uh, let's go and uh, again go on Discovery Studio. So this is our protein and ligand. So you can do what you can remove the structure and let's change it into again ribbon kind of structure. So delete it by selecting, then you will have this structure. So is it clear to everyone? Is there any problem you can ask? So that's it for today's session. If there is any problem or any queries, you can let me know. In this way, you can perform docking and you can visualize your result and save your image. Any queries? If no query, then that's it for today's session. So I will ask Professor Asadullah Khan for concluding today's session.
Okay, thank you, Nabila, for holding the session. And I must thanks for us the Abras technology. You can unshare the files. Uh, Nabila, you can stop the sharing. Well, so thanks to everyone, and I think I must thanks to the Abras Technologies who has organized this event, and it's good for the young students and the young learners. And I can understand it's in a 4 days. Uh, these four, 5 different themes that we discussed is very difficult to understand, but this is just like a preliminary understanding about the subject, say ABC. And when you start doing yourself, then probably you can have real hands-on training. And but this is just like a kind of a glimpse of the whole story. And through these lectures and through these hands-on sort of workshops as organized as instructed by Dr. Nabila and Dr. Afsar was really wonderful. And I think it was very comprehensive in a short time, more detailed information being given to all of you. I'm sure you must have an idea about what simulation modeling and docking, virtual screening, and sequence analysis, genomics is. And of course, a little bit about the recombinant DNA technologies in and out, and CRISPR-Cas, which is one of the most latest technologies being used in multiple domain, from therapeutics to identification of deciphering the pathways of several diseases, as well as several function of a gene is being studied. Uh, uh, so I thank you all for joining, and I think the certificate you can contact to the same email for your certificates, and your certificates may be ready in a day or two. So we'll provide the certificate email. Uh, I mean, of course, all participants will get the certificates. So I think this is all about. And I think if you have any, maybe one of you, one or two of you can come up with some kind of feedback so that we can try to improve this kind of lectures in the future. Uh, if any one of you can come up with the, maybe 2 students can come for the feedback. Although we can also get the feedback through in written, but I think on screen also you can discuss the feedback regarding the content, regarding the time for the content, and regarding the presentations our speakers made for you. Please, I'll give you 1 or 2 minutes to you. Who will come? Because some of students I'm seeing from our own biotechnology program, Safana, Nandini, Prerna, Ayushi, Shakshi, Huda. So I think if any comment or anything, feel free to discuss, because that way, things can be improved further to deliberate in more better way and presentable form. Yes, no comment, no feedback. It means the event was not good.
Good afternoon, sir.
Good afternoon.
So it was a really good initiative, like this workshop, and we learned a lot about obviously the basics, and it's. I think the problem is with the only problem is with this like online platform, that there must be technical glitch, and
Yeah, yeah, I
so
can understand.
that's the only issue with that.
I think offline workshops can also be organized, but I think in offline workshop, the strength is a question, the challenge for us, because we have a limited number of students, and
Sir, you are not audible.
yeah, maybe we can organize workshop in the future offline mode, but I think for that we have to have a limited number of students and some strong backup of the systems and servers. Okay, so anybody else, any comment? Sana, if you have any comment.
Yes, sir. It was a very nice workshop, and I'm very thankful to you, and I have learned a lot from this.
I think for UG and PG students at this level, understanding of these things are important. It is not important that you learn each and everything. Of course, it will take time. If you have interest in future for research and for some further work, then you can also contact us as a trainee in my lab. I can think of on it, and or some other way we can help you out. But I think this is good that to have a slight taste of about these areas, which is very upcoming areas in the biological sciences, especially in modern biology and biotechnology, you may call, or any field of micro and molecular biology, to explore research and to come up with some good and novel ideas. So we'll some other time meet and again and in touch and see what we can support you. Or okay, so thank you very much. Now I'm going to close it if there's no other comment. Thank you so much, and thanks to Dr. Afsar and thanks to Nabila for holding sessions and spending time and doing a lot of effort in organizing this kind of events. And I think this was really a wonderful event in terms of like presentation. The presentation made by Dr. Afsar and Nabila was really very good, very presentable and easy way, and the presentation was very good. I think I'm sure all of you will agree with me, and that's it. So thank you so much, and again I'm now close the meeting. See you again.
Yes, sir. One more thing I want to add: the
Yes,
lecture
yes.
from Professor Tanveer, I guess.
Yes, yes.
That was a very nice lecture. So if you will organize such lectures in future as well, so it will be very like we will get more
Definitely, we'll
exposure.
plan we may plan a separate workshop on CRISPR-Cas because my lab is also focusing on CRISPR-Cas, so we can also provide made a whole based CRISPR-based workshop in the future, and that too on focusing on different area, therapeutics and interventions and pathways exploring, knockout, knockdown, knock-in, all kind of things can be done in animal models and bacteria and viruses, right? We will make it. Okay.
Yes, so thank
Thank
you.
you so much. Okay.